start? Thank you very much. So welcome back. I'm a bit puzzled because I had an example in mind, but it does not work, so I won't tell you about it. And so I want to, today I want to give the proof of the theorem that I mentioned yesterday. So I tried to simplify it as much as I could. It's not difficult, just a bit, sometimes a bit tricky. But before I need to, so yesterday I defined delta hyperbolic metric spaces with using triangles, but there is a definition using quadrangles. So let me write it down. So I need my notes, I'm sorry. So the quadrangle inequality is the following: x, y, take 4 points, and if I remember well, thing like distance from x to z plus distance from y to w is less than the max of x, y, z, w. Yeah, okay. And the diagonals. And so I mentioned that because not for the pleasure of writing inequalities, but because I will be using it. And it turns out that this is equivalent to being, I'm sorry, I missed something, plus delta. So we are in a metric space like yesterday, and it is assumed to be delta hyperbolic in the sense that I defined with triangles. And it's not difficult to prove this inequality with 4 points. So you add these two, and then the diagonals. So I leave it as an exercise. Move it. It's 2 delta, I'm sorry. Of course, there are 2 triangles involved. And it's an easy exercise. If you are not able to do it, you can you can look in the book by Athanase. Even though it's written in French, you'll be able to figure out the proof. It turns out that, as usual, this is a consequence of delta hyperbolicity, but it could be a definition. So this could be exactly a definition. So it's really equivalent to the one I gave yesterday with the triangle. Okay. So let me recall the theorem that I want to prove today. Right. Yesterday it was easy, only presentation, but today I have to write proofs. So we're working with delta hyperbolic spaces. So one delta hyperbolic space. So this quadrangle inequality is satisfied. So for me, I recall that this implies that the space is quite simple actually. It's locally compact. Closed balls are compact, so it's proper. It is a geodesic space. Sometimes it's called complete length. Well, it is a geodesic space. Between any 2 points, there is a minimizing geodesic, a geodesic which realizes the distance. Maybe several, but at least one. And that's it for today. And we'll have, as usual, a group acting properly by isometries on the space. And our interest is really twofold. We want to understand the geometry of these metric spaces, which is a nice class because it's not too big and not small at all. But we also want to understand the properties, the algebraic properties of these groups, as usual, when they act on some geometric space. So it's acting properly, which means that in a closed ball, in a ball, there are finitely many elements of the orbit of the center, and by isometry on the space. And we're asking this to be big in the sense that there is a quotient. Right? There is a quotient with induced distance, and we assume this to be compact, and furthermore, we'll give a name to an upper bound of the diameter. And then came yesterday this new invariant, which I promised to explain a little bit more, but unfortunately today I want to finish the proof, and then I'll be kind of free. And so I spend 15 minutes, maybe tomorrow. I postpone every day to the next day, and there is a time when the next day I will be in the plane, and I'm sorry about that. So that maybe tomorrow I'll say more about this invariant and its interest in geometry and also in the study of groups. And so I assume that this is bounded above by some number. So bounded above because I want to study the class of metric spaces satisfying all this and want to get information only using these two invariants. So I recall that yesterday I tried to explain, I hope I convince you that this is a weak version, a very weak version of the lower bound on the Ricci curvature. So it replaces in our story Ricci curvature. So we want to prove compactness theorem without any curvature at all, which is good because these spaces might not be, certainly not manifolds. So the example I had in mind was not a manifold, but then 2 minutes before starting, I realized that it was not an example. Good. Tomorrow I'll give more. And then we prove some kind of so something which is a Bishop-Gromov inequality. So this is a measure, I will explain again what it is. And today I give a different version. Stop. Today I give a different version because it's simpler for the proof. So the radii are greater than 12 the delta. And for any point x, and we consider this counting measure on the orbit. I will come back on this in a second. And I want to prove that the measure of a ball of radius r, so the ratio between the volume of a big ball divided and the volume of a small ball. But the small ball here, for convenience, I will take it not that small, and I will use 5 divided by 6 r. Okay, okay, I'll explain in a minute. And then this is bounded above by 1 plus 6hr. No, this was yesterday's version. 1 plus 2hr. All right, so this is really a Bishop-Gromov inequality with two weaknesses. The first one is that we can only consider big radii, big enough, which is kind of normal in the sense that with the delta hyperbolicity doesn't say anything about the local geometry as I tried to explain yesterday. It's always true delta hyperbolic on small balls. So you can modify the local geometry, even the local topology, and get same kind of properties. So this should be reflected in the fact that you cannot say anything about small radii, and this is the case. And yesterday I present a result where you can say something about small radii, but you will have to add some more assumption, some more information on the space. And I recall to you that this is nothing but a counting measure. So this is just the sum of Dirac mass on the point of the orbit by the group of the point x. So when I write this, the volume of this ball for this measure, the measure of this ball is just a number. So let me write it again to recall what I did yesterday. It is just a number of element gamma whose displacement at x is less than r. This is what it is. What is the measure of this ball? Okay. Well, in fact, and this I want to prove, not even state. but let me mention it. A similar inequality is true for almost any measure, say reasonable, gamma invariant measure. So the one nice feature about this object is that it is invariant by the action of gamma. Of course, we sum over all gammas. And now you might ask what happens if we take any gamma invariant measure. So a similar result is true. Similar means that the constant might be different, but the spirit is the same. And I don't want to state this. What do I mean by reasonable? Well, we need that the measure of compact set is finite. And maybe the measure of big balls should be non-zero, because in the course of the proof, we'll have to take a logarithm somewhere. So reasonable is, and for example, if you are on a Riemannian manifold, the Riemannian measure is reasonable, of course, right? Okay. But this is just a remark, and it's written completely in our paper. But I don't want to write. I don't want to write a statement. Okay. So what else should I recall? So this is okay. This is okay. Good. So this notation is very heavy. So for this lecture, I will use mu instead of mu x gamma to simplify the notation. And so just remember that this mu is a counting measure, right? And this we'll use in the course, in the proof. Okay. So since this is a proof, there are lemmas, and there are technical lemmas. And I start by this, right? So I'll state two kind of easy technical lemmas, which I'll use in the core of the proof. So tell me if I forgot to recall anything. The comment that I wanted to make is the fact that Soma this morning explained how important it is to have a Bishop-Gromov inequality. She showed that you can say things about growth of groups. So this is very important to prove this kind of inequality. And tomorrow morning, Gilles will explain some consequences on the topology and later on the structure of the group. So that's why we have struggled that much to get this. So easy lemma. So two lemmas. I call them technical, but they are not really technical. So there is one which is really easy, which I love actually. So X is a metric space, a measurable metric space. Mu is a measure. It might be, it's quite general, but I'll state it in this context. And for any omega included in X, this integral, d mu y, is equal to integral over X of mu b y r. I'm sorry, this was r. Intersected with omega d mu y. Right? Or maybe I should change the notation just because we have two different integrals. Okay, like this. Okay, so this says that if you integrate this quantity on some subset of X, then this subset can come in the story here. And this I will use twice at least. This is trivial, so I leave it as an exercise. If you want a hint, is an easy corollary of Fubini's theorem. And we use here the symmetry of the distance. I say this because some people in this room do not like symmetric distances, but here we need it. Okay, so this is Z, and this is Z. Right? So this is Fubini, and the second lemma is a little bit more interesting geometrically, and it goes as follows, and I will not prove either, because I don't have enough time. We start with a delta hyperbolic space, of course, and we take two numbers R prime, positive, of course, which are supposed to become radii, and 2 point x, and we assume that the distance between x and y is less than r plus r prime, strictly less. Then we'll have to look at the intersection of these two balls. And I will draw a picture in a second. And we want this intersection to be not too big. So what does that mean? In fact, we'll show that there exists some y prime in x, so that this intersection is included in a ball around y prime and a radius which I call small r, which we can estimate. And the estimation is this one. The minimum of these three quantities. So most of the time, this minimum will be equal to the third quantity, which I'm going to write right now, r plus r prime minus d of xy, and of course, plus 2 delta. Right, so the picture is the following. If you have questions, please do not hesitate. I'm not sure I can answer all questions. I'm sure that I cannot answer all questions, but at least I can pretend that that is possible. Right, so x, y, and they are at distance r plus r prime. For the sake of simplicity, we can take r equal to r prime on the picture. So they are at distance less than 2r. So if I draw the ball of radius r around y and the ball of radius r prime around r around x, they intersect. And the question is, how big is this intersection? And the theorem says that in a delta hyperbolic space, there is a point. So actually, we can show it is here, so that this is included in a small ball, in a rather small ball. So in a ball of radius, this small r obtained like this. Right? And so this is an quite easy consequence of the quadrangle inequality. That's why I introduced this quadrangle inequality at the beginning. So I'm not going to give the proof, because it will spoil the rest of the lecture and your life, maybe. But this is a consequence of the quadrangle inequality. Instead of giving a proof, I would suggest, or you can try to prove this, but I'm not giving it as an exercise. But I would suggest to do the following exercise. So show that, one, it is not true in Euclidean space. Well, it's kind of clear, because if you take really big balls, then the boundary becomes like a straight line. And so you have to go very far to cover the whole intersection. But you have to formalize this. And secondly, show that it is true for the other space that we have been looking at yesterday, for a tree, for a metric tree. So this is an easy space, and do the same thing than what I did yesterday. You decide that the edges are isometric to an interval 0, 1. And so you understand these are always the two extreme cases, and any anything which is true for a delta hyperbolic space, you should first start to test it on these two cases. It's easy to do, right? Okay, good. So now I proceed to the proof, which I hope to finish, but it's not completely clear. So now there are lemmas that I will prove. Okay, are there any questions at this stage? No? Good. After lunch is a bit difficult. This is really interesting. Actually, this is a really interesting geometric fact, which is again, I'm not sure we completely. At least I'm not sure that I completely understand. But it's related to the fact that in negative curvature, the volume is concentrated on the boundary of balls. But this, I understand the proof, but I'm not sure I understand it completely at the moment. Right. So now let's start with real with lemmas that I will prove. Okay. So we come back with the original situation. Any question? Okay, thank you. So I'll use the notation that I described. Now we are on a delta hyperbolic space, and we will be only working with balls and integrals. So I have this measure, mu, on x, which I recall it is mu x gamma. And here's an inequality that we will prove. If we take two numbers with some constraints, which I'll write in a minute, we'll compute volume of annuli. And I draw a picture. Right? This is R prime, sorry. And this is less than, and this is, the formula is very long to write, but I will do it. The measure of the ball, of the annuli of radius r plus r prime and, I'm sorry, r minus 1 alpha of r prime multiply, and so since I need some room, I will put here the second term, mu, the ball of radius 3/4 of r prime plus 2 delta plus d. Okay. So what is this mess? Okay, so I compute this integral, and we'll see why later. And it is an upper bound is given by the product of measure of this ball around x and the measure of this annulus around x. So let me draw a picture to explain this. So we have a ball of radius r. R is supposed to be big, and it will go to infinity. And we have this r prime. So this is r. Right? This is r minus 1/2 of r prime. And the third one is this one. It's r plus r prime. Right? So we first compute the integral of this quantity on this small annulus, and then we compare to the big annulus, this one, times the volume of a ball in x. So what is the quantity that we are integrating here? For a point, this space, we are looking at a ball of radius r prime. Right? Well, we would love to say that it's that the integral is just the product of the volume of this annuli times the volume of this ball, but it's not satisfying for us. So what we want to do is to enlarge the annuli in order to include completely the ball. So we do this, but we don't include it completely because there is this point here. And here we will be using the lemma that I described before. So this can be included in another ball around some point y prime, for which we can estimate the radius. and hence estimate the measure. But we are not satisfied with balls which are not centered at x. So we'll try to move this one to x, or in fact to move a ball which is close to x, and that's where we get these fancy numbers here. So this is the main idea. And then we can write at least an upper bound of this integral as a product that we will use extensively later. Okay, are you ready? Let's do it. Right. So how does it start, actually? I wrote a first line which is stupid. It's not useful at all. Yeah. Okay, okay, very good. Okay, so let me start with this, which is the quantity that I want to estimate, right? Okay, so this, so rather than that, I will follow my scheme. So I will write this of y r prime d mu y on some ball b of x r, right? And I will decompose this into sum of on b of x r minus 1/2 of r prime of the same quantity, of course, mu y, plus sum on b of x r minus, but this one, b of x r minus 1/2 of r prime, and of the same quantity. So far I did nothing, but you see that if I put this on the other side, what I'll get is the integral of the quantity on this annulus, which is the term that I want to estimate. So this term that I want to estimate is equal to this one. So the only thing that we have to do is estimate this one. Right. So let me erase this. I hope that you are convinced. Difference of two integrals. Yeah, okay. So the important thing is that we are always working with balls centered at the same point, so that we get annuli when we make the difference. And here I'll use a fancy trick. So these are all concentric balls. And in particular, it is concentric with this one also. So I want to replace this by the larger one. But of course, it's not anymore the same integral that I had before. And in order to recover the same integral that I had before, I should intersect with b of xr, right? All these balls are concentric. So the intersection of this with this is equal to this one, and this is contained in this one. So what I have written is trivial. But you see, I have written, I'm sorry, this should be new. I have written this because of the lemma that I wrote, that I gave to you at the beginning, which says that you can put this inside here. So this integral, we can write, sorry, because of the previous lemma, we can write as b on bxr plus r prime minus bxr minus 1/2 of r prime of the following quantity, which is the measure of b of y r prime intersected by b of x r d mu y. So the quantity that we have to estimate, which was written here, is equal to this one, which is equal to this one. So now we have to work on this one. So let me erase the previous one. So at this stage, I've only done some easy stuff, right? Nothing fancy. Now I'll use what I know. So why did I wanted to consider this? Well, because if you take any point in B of x r plus r prime minus B of x r minus 1/2 of r prime, then the distance from x to y, of course, is less than r plus r prime. And it's not smaller than r minus 1/2 of r prime. And I realize that I forgot an assumption in the statement, but I will give it now. And this I write stupidly as r minus r prime plus 1/2 of r prime. So this is easy, right? And I forget the assumption, in the assumption, something which is important. I will assume that both numbers are big enough, and here big enough is 8 delta, right? So this will be greater or equal to r minus r prime plus 4 delta. Okay. 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 So it's not difficult. So come back to the technical lemma. I leave to you to check that there was a small radius r, which was the minimum of something, and that the minimum is achieved here. So the technical lemma tells us now that there is a point y prime and a radius r, so that the intersection of the ball of radius x, ball of radius y, with different radii, is included in the ball of radius small r around r prime. Right. Well, it's not difficult to show that the minimum is achieved for the third term in the equality, and so the radius here is just, so what is this number? The radius is 1/2 of r plus r prime minus distance of xy plus 2 delta. So I really want to compute the radius quite closely. And yes, we can input this inside. I guess it gives something interesting. And does it give something interesting? Yes, I guess so. Right. Right. So this is what I've written on my paper, is that this is less than 3/4 of r prime plus 2 delta. Right? Is that correct? Yeah. Okay. Distance comes from this. It comes from this. So you replace this distance. There is a minus sign by this. So the r will cancel. R prime there will be twice, but there is 1/2 here. 4 delta will become 4 delta will become 2 delta, and there is too much of deltas here, so I just made a mistake somewhere, but you see here it is 2. No, here it's 4, but okay, sorry, I just make a mistake somewhere, and I leave to you to finish the proof here, right? So this 2 delta is here, and 3/4 of r prime. I don't remember how it works. Anyway, anyway, we can estimate the radius of this ball here, and so now it's finished actually, right? It's almost finished. So let me write the rest of the inequality. So the quantity that I want to estimate is this one. I will write it here. And this is mu of b y r prime intersected with B of X R d mu y. And what we have shown is that any point here, any point y which is here, is such that this intersection is included in a ball around some point, y prime, of radius 3/4 of r prime plus, so what was the number of deltas? 2 delta. So it was a little mess with the computation, but on the board it's difficult, and so I suggest that you use all the inequalities to find this number. But then this measure is less than this one. Still, as I said before, I'm not satisfied because this point is not x, right? So how can we replace this point by x? Well, there is a trick that I will be using several times, and which is the following. We have one assumption that we have not used at the moment, the assumption that there is a compact quotient. A compact quotient means that for any point here, there is a translate of x by one element of the group, so any point z. There is a translate of x by one element of the group so that the distance is less than d. Right. So in particular, for this y prime, there exists an element gamma prime so that the distance between y prime and gamma prime x is less than d. Well, it's obvious because if you project y prime and x onto the quotient, the projection are a distance less than d, which is exactly translated here. Right. So finally, this ball, b of y prime 3/4 of r prime plus 2 delta, is included in the ball around gamma prime x of radius 3/4 r prime plus 2 delta plus d. This is a number that we had in the statement, right? And we'll take the measure of them inside here, which is an upper bound of the measure of this one, and an upper bound of the measure of this intersection. Right. Now the measure mu, I recall that mu is mu x gamma, is invariant under the action of x. And this ball, which is centered at gamma prime x, is a translate of this ball of same radius around x. So this ball here is gamma prime applied to b of x 3/4 of r prime plus 2 delta plus d. So that's how we use the group, right? So the measure of this is equal to the measure of this, but because the measure is invariant, it's equal to the measure of the ball x 3/4 of r prime plus 2 delta plus d. So finally, an upper bound of this quantity is the integral around this, the integral on this annulus of an upper bound of this quantity, which is the measure of this quantity, which is bounded above by this, which is equal to this and this. Plus 2 delta plus d. Okay. But here we integrate on y, and x is fixed. So this is just a product. R prime plus 2 delta plus d times, well, the measure of this. Let me write it, although it is clear. And this is what we wanted to get. So there is nothing fancy, although I was able to mess around with the numbers, but believe me, the result is correct, and you can adjust the proof. And there is nothing fancy, except that we have this technical lemma in the middle, which is related to geometry and which tell exactly how to control these kind of things. Right, so the first lemma is proved, then there is a second lemma which is much simpler, and then we are done, almost done. And I will have time to finish. Right. Okay, I know it's boring. But I want to do the proof completely. All right. So the second lemma is much simpler. And same hypothesis for all x in X, for all R prime R, which are greater than 12 d plus 2 delta, the bound that I had before. Did I have 12 or 10? It depends on which kind of measure we consider. So I put 12, I guess. Right. Then the measure of the ball centered at X and of radius R prime divided by the measure of the ball centered at X 5/6 R prime, which is the quantity that we want to estimate. Then this is controlled by measure of annuli. In particular, measure of X R plus R prime minus the measure of ball centered at X R minus 1/2 of R prime. So this is the biggest annulus divided by the measure of X. This is R minus the measure of X R minus 1/2 of R prime. So the quantity that we want to estimate, and this is a corollary of the previous lemma, so it's a ratio, but it's also bounded above by the ratio of the volume of this big annulus divided by the volume of this small annulus. And what we'll do later is to accumulate these annuli. So R prime will be fixed, and we let R goes to infinity, or rather we'll accumulate some of them. So we'll have two annuli, which looks very much like balls, whose radii are going to infinity, and we know that this is related to the entropy. So the growth of this volume will be controlled. We will give an upper bound in terms of the entropy. On the other hand, because of this inequality, the growth of this quantity, when we accumulate it, is controlled from below by this, or some power. And this seems to be a contradiction, but this will give the right inequality that we are looking for. All right, so let me do this. Believe me, it's painful for me too. I have a remark to make, so that I used. So let me insist on this remark. The measure is invariant. So for any radius, this measure applied to a ball centered at a point which is on the orbit of X is equal to the measure of the ball of same radius centered at X. Huh? So there is, and the reason, let me recall the reason, is that this is the image by the isometry of this quantity. And the measure is invariant. So this we'll use several times. All right. Right, so I want to prove this inequality. So I take this, multiply by this, and show that it is this multiplied by this. Cannot be easier. How many people do I have lost already? No, everybody is following. Okay, very good. Thank you. So let me write some inequalities. So what I want to understand is this times measure ball centered at x and of radius r minus ball centered at x and radius r minus 1 alpha of r prime, right? And this is right, and this is equal to this is stupid. So this is a product. This is equal on integral on this ball of this. I'm sorry, it's r. No, it's r prime. X r prime d mu y. So this is stupid. This is independent of y, so I put it inside some integral. It's r prime. Right. But now this, so this is a subtle point. So this measure here is the sum of the Dirac mass at x, measure mu. Since I decided to call it mu, this counting measure on the orbit, right? So in this integral, the only y that counts are point on the orbit gamma of x. But for point on the orbit, this ball is isometric to the ball on gamma x. So I can replace this by, I'm sorry, it's a measure, of course, I'm sorry. The same integral, but with the measure y prime of y r prime, d mu y. Because the support of the measure is always, in this situation, the support of the measure is always the orbit. And these quantities are equal. When y is in the orbit of x, they are equal. So I could replace this integral where there is a constant here by a constant but written in a different way. And this is the trick that I will be, the last trick that I will be using. Right? Okay. Okay, but then it's finished. Then it is finished because, then it is finished because this is the quantity that we had in the previous lemma. And in the previous lemma, we showed that this is bounded by mu of this, which I don't want to write. Let me write, because in the previous lemma, we showed that it is bounded by mu of r plus r prime minus ball around x r minus 1 alpha of r prime, so it's an upper bound, times measure of the ball of radius, so what was centered at x, of radius 3/4 of r prime, plus d plus 2 delta. Okay, so we have r prime here. We are almost done. So we are working on the denominator. Unfortunately, there is this. But r prime is assumed to be greater than 12 times d plus 2 delta. So this is greater than a ball around x of a larger radius, which is 3/4 of r prime, plus 1/12 of r prime. And if I'm not mistaken, 3/4 plus 1/12 is 5/6. Okay, so you see it's just an application of the previous one. The only trick is this one. You have to understand that when we use this counting measure, then the balls of the same size, of the same measure on the orbit. So the other points, if y is not on the orbit, it's not in the support of this measure. So then it will not be considered in this integral. Okay. So now we will finish the proof of the theorem, and it's much more reasonable. Okay, do you have any question at this stage? Yes? Ah. Thank you for asking a question.
So what is the meaning of the third line from the third line in the middle?
This one?
No, upper one? Yes.
So the meaning, what do you mean? So this is equal to this because this quantity does not depend on y. So this becomes, it's a constant. It's a constant times the volume of the ball. Is that your question?
I mean, here you integrating this ball of radius r dash over this.
So I'm integrating the measure of this ball, which depend on y, but there is no y here. So it's a constant number. So I'm integrating a constant on this space. So this is equal to the constant time the measure of this space, which I had here.
Yes.
And the reason why I wanted to do this is to go to the next step using this invariance by the group. This is the trick which allows to do it. But this is completely trivial. I understand that this stage of this time of the day is difficult to follow, but right. And then the upper bound is coming from the previous lemma, and this here is just a stupid remark that 3 over 4 plus 1 over 12 is 5 over 6. Yeah. Thank you. So let me finish the proof of the theorem. Now we work with this inequality, and we'll try to do what I said in the introduction of the proof of this second lemma, that we are going to accumulate the annuli. So now I can go quickly because these are only very elementary things. So we'll replace R by, so we keep R prime and we replace R. So I'm trying to check that I'm not saying a stupid thing, by K R prime over 2. You see, I want to construct a sequence. So this quantity is fixed. It does not depend on this K. R prime is fixed. So here we'll have K plus 2 R prime over 2. Here we'll have K minus 1 R prime over 2. Here 2 R prime over 2. Right? And here we'll have K R prime over 2. So if I define a sequence AK, which is mu of the ball of centered at X and of radius R, which is the same thing than mu of the ball centered at X and of radius K R prime over 2 by my choice of R, then here we have an inequality which is A K plus 2 minus A K minus 1 divided by AK minus AK minus 1 is greater than this fixed quantity, which for the sake of convenience I will call C plus 1. I subtract 1 for some reason that will be clear in a minute. So it's greater than 1 plus C. So we get a sequence that satisfies some equation. I love equations. So I don't know the name. It's defined recurrently, and so, yeah. Yeah. And so I can get rid of this one here. Right, AK minus 1 will so if I want to get rid of this one, I will get AK plus 2. I just expand AK plus 2 minus AK is greater than C time AK minus AK minus 1. Right, so there is C time this quantity, which appears here, and 1 time this quantity, which I switch on the other side, and the minus AK minus 1 will become a plus, cancel this one, but it will be replaced by minus ak. And we have a beautiful equation. Now we sum for all integers between 2 and n. So they cancel one with, well, here they cancel one with the previous one. It's a classical. Here there is a jump of 2. So the two largest and the two smallest, they remain. So what we get if we sum on this is a n plus 2 plus a n plus 1 minus a3 minus a2 is greater than c a n minus a1. Right? You see the stuff, it's easy, right? You can solve. So these are measures of balls. So it's increasing, while non-decreasing. So this is, wait a minute. Yeah, it's correct. So it's non-increasing, so it's not decreasing. So this is less than that, so I can put 2an plus 2. And this is greater than a1, and this is greater than a1, so minus a1, like this. So we get the same and here. So we finally get minus a1 greater than c over 2 an minus a1. Right? Easy so far, and it's finished now, of course. And, well, then you iterate 2 by 2, and what one gets is a2n is greater than c over 2 to the n minus 1, a2 minus a1, or a1 minus a0, a2 minus a1, plus a1. Okay. So the point is that this inequality yields what I have tried to say, that the growth of this ball, the measure of this ball, is exponential with a quantity that we control, quantity which is given by this. On the other hand, the growth of this ball is bounded above by the entropy. So it's bounded below, it's bounded above, so we get an inequality. So let me finish. I still have 3 minutes. And so to finish, the entropy, this number h, which is greater than the entropy of the space, so I forget the measure because the measure is fixed, is equal to the limit when n goes to infinity of any subsequence of radii, so in particular 1 over n r prime, logarithm of mu of the ball centered at x and n r prime. Just because the entropy is a limit in that situation where you have any r here, so you can choose a subsequence. Right? But this is a2n with this definition. So this is equal to the limit when n goes to infinity, 1 over n r prime, logarithm of a2n, for which we have an estimate. And that gives the estimate by taking logarithm and letting n go to 0. We get then 1 over r prime logarithm of c over 2 is less than h r prime, right? Which gives c plus 1. So c is less than something, and I add 1 plus 2 e to the h r prime, which was the quantity that I wanted to get to prove this weak version of Bishop-Gromov. Right. So there are two issues that I have 1 minute to explain, 45 seconds. 40, too bad. There are two issues in this story which I want to explain, and I'll take 2 minutes. This should not be 0. I'm taking logarithm, it should be positive, and this should not be 0 because it will, otherwise it will cancel this. So let me explain this, and the second one is of the same nature. So what is C? C is, so where should I write this? C is the measure of ball of radius r prime by the measure, divided by the measure of a ball of radius 5/6 of r prime, and -1. So we need to show that this is strictly greater than -1, right? So we have two balls here. Let's look at the annulus between these two balls. There are open balls. The annulus is closed on one side and open on the other side. So the size of this annulus is 1/6 of r prime. So into this annulus, there certainly is a point y and a ball around this point of size, well, the half, 1/12 of r prime, right? But 1/12 of r prime by assumption, and this is where the assumption comes also very strongly, is greater than, so it was the stuff 12d plus 2 delta, which is then strictly greater than d. So again, we use the same trick. It's strictly greater than the diameter. So there is a point in this ball of the orbit of x. So there exists in this ball a point gamma x. But this measure here does count points of the orbit. So there is one point of the orbit of x which is in this ball and not in this one because it is in the annulus. So this quantity is greater than 1 plus this one. Mu bx r prime is greater or equal to mu bx 5/6 of r prime plus 1. Okay, so if we divide this by this, will be greater or equal to 1 plus a small quantity which is positive. So this is strictly positive. So this is one of the reasons that we had to choose this size to adjust the proof. And the second point, that A2 minus A1 is non-zero, is the same kind of things because A2 minus A1 is the measure of an annulus. Difference of measures of ball. Okay, good. So we did this proof, right? Thank you very much. I stop here. What is it, tea time, coffee? Excuse me? Ah, sorry, so it's our theorem. Ah, so the theorem with, you know, it's written in the sheet of paper. So you are seated nearby Gilles Courtois, who is giving this course with me. He will be talking tomorrow. And other collaborators are Gallo and Andrea Sambuzetti. Sorry. Any other question about names? Okay, so maybe we should have tea or something. Yeah, okay.